Now, let us discuss ground wave, first mode of propagation, that is ground wave propagation. Okay, so I have already told that by using this ground wave propagation, wave propagation, I can transmit any signal less than 2 megahertz. Okay, any signal. So, what is the coming to the diagram of the ground wave propagation? This is my transmitting antenna. This is my receiving antenna. So this ground wave follows the curvature of Earth surface. Follows the curvature of Earth surface. Okay. So the ground wave or surface wave is used for broadcast and lower frequencies. Lower frequency is less than 2 megahertz. That is for medium wave, long wave, and very long waves. Okay. So the ground wave is the wave. The ground wave is the wave that is guided along the surface of Earth, surface of the surface of the Earth, surface of the Earth, or follows the curvature of the Earth, or follows the curvature of the Earth, curvature of the Earth as an electromagnetic wave is guided by a waveguide or transmission. Okay. So surface wave permits the wave to propagate along the curvature of the Earth. Okay, so this mode of propagation exists when the transmitting antenna, and receiving antenna are close to the surface of the Earth, and supported at the lower edge of the presence of the ground. Okay, so the ground waves that is being generally produced, the ground waves that are produced by vertical antenna is vertically polarized. That is, the electrical fields, the electrical field vectors of electromagnetic waves are vertical with respect to the ground. Okay, so see here. Now, for example, this is my Earth surface. This is my Earth surface. This is my transmitting antenna, and this is my receiving antenna. So, for example, I have transmitted any signal less than 2 megahertz. Okay. So, as I am transmitting along the curvature of the Earth surface. Okay, so any ground wave propagating along the surface of the wave induces charge on the Earth. Okay, which travels the wave and hence constitute the current. Okay, so while carrying this induced current, the Earth behaves just like a leaky conductor. The Earth behaves like a leaky capacitor. Leaky capacitor, and therefore the Earth can be represented as a resistance in shunt with capacitor. So the Earth can be considered as a resistance in shunt with a capacitor. This behavior of this Earth as conductor may be described in terms of conductivity and dielectric constant. Okay. So whenever the surface wave, for example, the wave is moving like this. Okay. Whenever the wave is moving like this, the Earth, since the Earth acts as the capacitor, it tries to absorb the signal. Okay. So if the distance between transmitting antenna and receiving antenna is very, very large, okay, the Earth before for example, so the signal strength slowly reduces sometimes before reaching to the receiver. Before reaching to the receiver, it may die. Okay, so since as frequency increases, okay, so for less frequency, the percentage for less frequency signals, the percentage of absorption of signal by the Earth is less. So we can communicate between transmitting antenna and receiving antenna, but at the same time, some of the signal strength will get reduced. Okay, but as frequency increases, means greater than 2 megahertz. Okay. So the absorption rate, the absorption. So let us consider this is my transmitting antenna. This is my receiving antenna. If I am transmitting any signal greater than 2 megahertz very close to the earth surface, what happen? So if I transmitting, so very close to the earth surface, the absorption rate of the earth, the signal it will absorb very quickly. So before going to the receiver, okay, the signal will get died off. The signal will get died off. That's why we are not preferred to transmit high frequency signals greater than 2 megahertz very close to the earth surface due to the property of earth attraction or absorption. So this is one disadvantage. Okay. Similarly, so another problem is there. Okay. So besides the ground attenuation, the first one is ground attenuation. The first one is ground attenuation. Due to this ground attenuation, what happened? I cannot transmit high frequency signals very close to the earth surface due to the absorption ratio or attenuation. Okay. So along this, we are having another problem. We are having that is another problem. The other problem that is faced by ground wave propagation is wave tilting. Wave tilting. Wave tilting. What is meant by this? Wave tilting. For example, let us consider this is my earth surface. This is my earth surface. Okay. Okay. So consider this is my transmitting antenna. This is my transmitting antenna. So as the signal is traveling in this direction, as the signal is traveling this direction, the wave will get tilted. The wave will get slowly tilted. Okay, so you consider it as a W. As the wave further moves, the wave further moves, the wave will get tilted. So this is a double dash. This is W. Now if you observe here, fourth case, this is my wave. Okay, and this is a double dash. Okay, so see here. Initially, how is my wave? How is my wave with respect to the earth surface? It is perpendicular. So initially at A, my electrical field strength is perpendicular. As the wave curve, as the this is the E tangential component. As the wave moves here, this is the second step. This is at A dash, and the third step, this is A double dash. And at fourth step, how is my wave? C tangential component is parallel to the ground. So we know that on the boundary conditions, E tangential is equal to 0. E tangential is equal to 0. So means if the distance between transmitting antenna and receiving antenna is very, very high, okay, what happened? The wave gets sliding, tilting, and finally the electrical field component is becoming 0. Means the electrical field component is becoming, initially it is perpendicular with the earth surface. Slowly as the wave grazes, if the distance between transmitting antenna and the receiving antenna increases, the wave slowly tilts on the electrical field component, that wave will becomes like this on the earth surface also like this. Okay, so how the earth surface and the electrical field component, they are parallel. So E tangential component is equal to 0. Okay, so beside the ground attenuation, there is still another way in which the wave get attenuated, that is due to diffraction. That is due to diffraction and tilting. Diffraction and tilting of the wavefront. Okay, so as the wave progresses over the curvature of the earth, okay, the wave front starts gradually tilting more and more. The increase of the tilt wave makes more short circuited of the electrical field component, and hence the field strength goes on reducing. Ultimately, at some distance from the transmitting antenna in wavelength, the surface wave dies before reaching to the receiver, because initially the electrical field component with respect to the earth surface is like this. Okay, so slowly it will comes like this, and one situation comes here, the electrical field complet is parallel with this E tangential becomes to the zero. Okay, so these are the two problems. Why are here? So for a why this transmitting antenna and receiving antenna, we cannot transmit more signal along the curvature of the X surface, along the curvature of the one surface. And similarly, we have seen in the previous one, high frequency signals I cannot transmit using uh, ground wave, because as frequency increases, the rate of absorption by the earth increases. Okay, so the rate of absorption by the earth increases. Okay, so the field strength. Okay, so the field strength at the distance from the transmitting antenna, the field strength. Let us consider this is transmitting antenna. This is receiving antenna. HT is HR. Okay. The field strength at a distance from transmitting antenna to the due to ground wave has been calculated using Maxwell's equation using Maxwell's equation as E is equal to 120 pi HT HR IS by lambda T. Okay, so units are, what are the units of volt? For example, this is, so what is the electrical signal? Oh, this is my earth surface. Okay, so this is my transmitting antenna. This is my receiving antenna. HT indicates height of transmitting antenna. HR indicates height of receiving antenna. And D is separation distance between transmitting antenna and receiving antenna. So the electrical field. So how much of electrical field signal I will get from transmitting antenna to receiver? It is given by Maxwell's equation, that is 120 pi into HT into HR, where HT and HR are the effective heights of transmitting and receiving end. And what is this D? D is separation distance between transmitting and receiving the antenna. Okay, IS is antenna current. IS is antenna current, and lambda is wavelength. Okay, so if you observe here in this equation, if the distance between transmitting antenna and receiving antenna increases, means if D increases, what happened to the electrical field? Okay, no doubt the electrical field decreases. So as the distance between it is the reduction in electrical field strength due to the ground wave. Uh, the electrical field strength is reduced, and whatever the signal you are transmitting from transmitter to receiver, it will decreases. Okay, so it is decreases. Okay, so these are all the things regarding ground wave propagation. So by using ground wave propagation, I can transmit any signal less than 2 megahertz. Why I can't transmit the high frequency signals? Because more as frequency increases, there will be more absorption of the signal by the earth surface. Similarly, there is another problem, that is wave diffraction and tilting. Okay, initially it will be like this. As it goes on, the wave will get tilted and it will becomes parallel to the earth surface. So E tangential becomes 0. Okay, so the electrical field strength for ground wave is given as ET is equal to 120 by HT HR IS by lambda D. If the distance increases, the electrical field also reduces. Okay, these are the things you want to remember for ground wave propagation. Ground wave propagation.